All right, let's talk about quantum theory. To really get our heads around it, we have to take a journey. A journey from the world that feels normal and predictable to a world that is, well, bizarre, but also completely true.
You see, our everyday common sense is great for, crossing the street or catching a ball. But when we zoom way, way down to the level of atoms and particles, that intuition just completely breaks. As the physicist Steven Weinberg said, it's a profound departure from everything we think we know.
So here's how we're going to tackle this. First, we'll get a feel for just how different the quantum world is. Then, we'll rewind and look at the old rules of physics it replaced. We'll see where those old rules started to crack, then dive into the strange new rules that took over. And finally, we'll see why any of this matters in our daily lives. All right, first up, this profound departure. I really want to emphasize this. We are literally leaving the world of common sense behind. This isn't just learning a new bit of science. It's about rewiring how we think about reality itself.
It's like this. You throw a baseball, you know where it is, you know how fast it's going, and you can predict its path. Simple, right? But down at the scale of a single electron, those rules just stop working. They completely fall apart. And that feeling of, wait, that can't be right, is what makes quantum theory so tricky, but also so incredibly cool. So to really appreciate how wild the new rules are, we first have to understand the old ones. Before quantum mechanics came along, scientists saw the universe as this giant, magnificent, predictable machine, a kind of clockwork universe running on the rules of what we call classical physics. And for a long time, this worldview, made famous by Isaac Newton, worked perfectly. It was deterministic, hit a billiard ball this hard, and it will always do the same thing. It was predictable. If you could just know the position and speed of every single thing, you could predict the future forever. And it assumed you could be infinitely precise. You just needed better tools to measure things more and more accurately. It was all very neat and tidy. But then, around the turn of the 20th century, scientists started poking around at the atomic level. And that beautiful, perfect clockwork model, it started to show some serious cracks. The old rules just couldn't explain what they were seeing down there. And it happened bit by bit. First, in 1900, a guy named Max Planck found the only way to explain the light from hot objects was if energy came in little chunks, or quanta. Then Niels Bohr realized electrons and atoms could only have certain specific energy levels, not just any old amount. And then Louis de Broglie came along with a truly bizarre idea. What if tiny particles, like electrons, could also act like spread-out waves? Each discovery was another nail in the coffin for the old clockwork universe. So this first big crack in the foundation is called quantization. And honestly, it's a total game changer. The best way to picture it is to think of energy not as a smooth ramp you can stand anywhere on, but as a staircase. An electron can be on step 1, or step 2, or step 3, but it can never be in between the steps. Energy, at its most basic level, comes in distinct packets. Now, if you thought that was weird, buckle up. The next idea is wave-particle duality. And yeah, it is as strange as it sounds. An electron isn't just a tiny little ball. Sometimes it acts like a particle, a single point. But other times it acts like a wave, all spread out. The craziest part? It's somehow both at the same time. And what you see, a wave or a particle, depends entirely on how you look at it. Okay, so the old clockwork universe is basically shattered. So what now? Well, in its place, a whole new set of rules had to be written. And these new rules are all about uncertainty and probability. So if that nice, predictable world is gone, what are the new rules of the game? What guides the universe at this fundamental level? Well, first up, we have the famous uncertainty principle. It basically says there's a cosmic trade-off. The more you know about where a particle is, the less you can know about where it's going. And the more you know about where it's going, the less you know about where it is. Now here's the kicker. This isn't because our instruments are clumsy. The universe itself has a built-in rule that says, sorry, you are fundamentally not allowed to know both of these things perfectly at once. And that uncertainty leads us right into the next mind-bending rule. The universe runs on probability. Quantum mechanics doesn't tell you exactly where an electron will be. Instead, it gives you a cloud of probability, a map of where it's likely to be. Before you look, in a very real sense, the electron is in all of those possible places at once. It's only when you make a measurement that it seems to pick a spot and appear there. So let's just put it all together side by side. The old classical world was deterministic, predictable, and precise. The new quantum world?
It's probabilistic, it's fundamentally uncertain, and it's quantized, built from the little discrete packets. It's not just a small change. It's a complete revolution in how we see the universe. Now, I know what you might be thinking. Okay, this is some seriously weird, abstract stuff. What does it have to do with my life? Well, it turns out, everything. This strange theory is the bedrock of our entire modern world. That computer or phone you're on right now? It's powered by billions of tiny switches called transistors. And transistors only work because we understand the quantum behavior of electrons. Lasers? Same deal. LEDs, MRI machines, nuclear power. All of it comes from understanding these bizarre quantum rules. And it's also the key to the future, with things like quantum computing poised to change the world all over again. So we'll leave you with this final thought. Quantum theory isn't just a wild guess. It is one of the most tested and successful theories in the history of science. It works, but it forces us to ask a pretty profound question. If the very foundation of everything isn't solid and certain, but is instead a shimmering, uncertain world of probabilities, what does that really say about the nature of our reality?